function to find out which direction makes that number smaller, we can just kind of like go that way. And if you have like a complex function, you know, that like has like a bunch of like local minimums, like say you're like over here, you don't want to get stuck here, you can kind of just like overshoot. You can just go like really far this way, and then you'll like probably like eventually, if you start like jumping back and forth enough, eventually you'll probably end up like somewhere pretty decent, right? Because you can probably assume that the like actual function looks like a little bit more like, you know, like this, right? There's like kind of like some sort of like wiggliness to it, but like overall it's probably trending towards some sort of like nice little area in the middle, right? So that's kind of hand wavy what we're trying to do. So how do we come up with that? Well, let's kind of make some new space. Um, so we have, what do we talk about? We have like three things. There's like loss, right? How wrong am I? There's the like this squiggly function. They call it activation. Activation. And then there's like the like multiply adds, right? Mul plus add. And it turns out, hand wavy, ReLU, yeah, you can have like many options here. There's like sigmoid is what I was looking at, was talking about, but there's like ReLU, there's a bunch of other ones. Basically something that like turns things on and off, but also is differentiable. Then there's like the multiply add part, which is like, you know, the weights and the biases times like the numbers that we start with. So if we want to know how like, if we want to know how like number weight 1 contributes to the total loss, there's this like thing in calculus called chain rule. We don't have to think about it as a rule. We can say, hey, there's like a bunch of steps happening here, right? Imagine that you have like x squared, right? Derivative of this, you take like first year calculus or like grade 12 calculus, whatever. The rule is like, for some fucking reason, if you want to know the slope of x squared at any point, you just like take the power and move it down here, right? So the x the slope of this function at any point in x is 2x, right? Now, let's say that x, though, we got x by doing a bunch of other shit, right? So maybe we have like some parameter y, we say y multiplied by 5, 5y, and then we square this thing, right? Well, we know that the slope of this thing is 2x, and the slope of this thing is like kind of 5 times whatever the slope, right? Any change in y is going to have like 5 times the effect in this scenario, right? And so it turns out that the derivative of this guy is 5, and so if you just like multiply the derivatives together as you like stack operations, that can tell you how much like that thing contributes to the thing at the end, right? So while, you know, change in x results in like 2 times the slope, the slope at some point here is hold on. Slope at this point is essentially like how much do we change if we walk in forwards, let's say, right? So in this guy, it's like we walk 2x. Yes, we're gonna move 2 times x in some distance, but then like that number is multiplied by 5 because we were having 5 times the effect. Hand wavy. So what we need to do is we need to figure out the derivative of each of these guys and just kind of like chain them backwards, right? So back to our little example of you have 2 numbers, you're adding these together to some output. This is turning into, you know, weight 1, weight 2, times like parameter plus bias 1 plus bias 2 times parameter 2, right? So these guys are all both going through like activation function, and that's going through, is that it? Then we're calculating loss. Yeah, something like this, loss. Yeah. Yeah. So you can just like chain these derivatives backwards. And so what we need to do is like keep some sort of graph, I think, of like how each parameter is getting like you know, if we want to know, we want to change weight 1 here to kind of like bump this thing down, this loss function downwards, we kind of have to like keep the chain of events that happened. That's my current understanding. I don't fucking know. Let's just fucking run it and figure it out from there. Okay? Let's figure it out from there. So, the plan of action is we're gonna like build the graph going forwards as we like, we forgot to add the P2 into loss. Yeah. Well, yeah, true. The loss is like sum of like all of these guys, right? Act, you know, parameter K times weight K plus bias K or whatever, right? From like K equals 0 to like param num or whatever. Right? Something like that. Whatever. I'm looking at this, I'm a little unsure about derivative of the loss function. I might have to look that up when we go a little forwards. I'm not 100% sure. My mental model, I'm not 100% here. Because, like, I don't know if the loss function has to be differentiable. I guess it probably does. I guess it does. We'll get there. We'll get there. We'll figure it out. But first, we need to figure out what set of operations results in something happening. And so, I think the plan is, I don't know, build up a graph somehow. Now, later it will be easier to think about these things in terms of batches of numbers, because that's what, like, when we eventually get this stuff onto the GPU, we're gonna have to do it that way. But for now, I think it'll be easier to do it this way, to just like do, you know, one number at a time, because I can only think about one number at a time because my brain's super serial, unlike GPUs, which are super parallel. Okay. Here's our library name, Smelly. Because it kind of like sounds like ML, and then we throw a SPH in front of there, and I think it's funny for us to be smelly. You know? So let's do that. Fruity Pebbles ass, yeah. Stupid cereal brain. So only Cheerios and Fruit Loops up there. Okay. I don't know. Let's do something. Let's make a main. Every program starts at main, and we write an error out here so that we get like some free standard out, zig, run, source, main. Hell yeah, dude. Uh-oh. Okay, so we want to build something that looks... Where's our little picture? Hello? Our picture was 2 parameters, 1 output. We need to make this. So, we have, yeah, I guess we have, you know, weights. Sure, we have weights that I guess in this scenario is like 2 floating point numbers. And we'll initialize these with random numbers later. We have biases, which I think actually probably aren't needed for this problem, to be honest. But, you know, this is the typical neural network thing, so we'll do that. Yo, that's my brain is a very funny message. And then, what are we doing with these things? We are, I don't know, we're like doing, I guess we have 2 numbers. So I guess we'll take these from standard input? No. We'll have to take these from somewhere. So maybe we like define a network. That feels a little bit more reasonable with some weights and some biases. Okay. Okay, and then we can like use this network for training somewhere and then for like execution later, right? So if we are in, I don't know, let's say that we look at the standard input. I guess we make the network here. Let's start there. Easy. And we probably need to like initialize these with some random weights. Yeah, let's do that. Here we go, we're getting somewhere. I think I'm just gonna delete this link because I don't want to look at it, and I don't really trust that it is, I don't really trust it. But not be, you know, not to say that you can't post links, just that I don't really want to look at it right now. you know, are going to be initialized with, well, let's figure out initialization later. We can just ignore that. Yeah, let's do that. Let's just do that. We ignore it. When we run this network, we're gonna run it with 2 input parameters, right? 3 and 10. Yeah. Yeah. And this guy is gonna have some sort of output, which, according to our very complicated graph, is 1 floating point number. Okay. Here we go, we're getting somewhere. And what is he gonna do? He's gonna say, let's run this by multiplying these guys together. So we say self, I guess it's self here, with, you know, A and B. We're gonna be like, weights 0 times A plus biases 0. Yeah. Hold on, we're getting somewhere. We take these guys, and then we add in, you know, the second weight and bias. So slap one of these on here. Okay. Yep. And then all of these guys go through the, like, you know, this function, which is called sigmoid. Okay, here we go. What's sigmoid? Let's look it up. I don't fucking know, man. Sigmoid. 1 over, here we go. E to the x over 1 plus e to the x equals 1 minus sigmoid negative x. Okay, sure. So we just pick one of these. 1 over 1 plus e to the negative x. Okay. I'm sure this will become more complicated later. Slap on a ReLU. Yeah, I mean, I think that it's easier to think about with sigmoids, but I do think that later we will change to ReLUs. I have to, like, do some reading on, like, why. My understanding at this point in time is that ReLU is, like, a cheaper activation function that's, like, less obvious. But, like, it doesn't really matter. It, like, ends up with training faster with maybe some more parameters, but, like, maybe faster training. I don't really know. Okay, so this guy takes in F32. And he returns an F32. Okay. And then we're like, return 1 over 1 plus, we probably need the sound library here. Stud math exp, right? This is base e exponential to a floating point number to negative n. Easy. Easy. It's simple. Simple. So this is what we're trying to make. Now, can we say const output is this, and then can we run this thing? So or print it. Okay. That's looking like you're getting somewhere. Now, why is he mad? Because we didn't use B here. We used A, like a dumbass. Easy, okay. So now we have to, like, initialize these things. So let's just initialize them with, I don't know, zeros for now. Random numbers would be better, but I don't want to, like, pipe a PRNG around there. Since you've done some graphics, the structure of the multiplication has the same commonalities with homogeneous coordinates. It's basically mat, weights, biases times vec vars 1. Yeah. Do you need the homogeneous in there? I thought that you could get away with, like, I think that it's just weights times biases, I think. But I could be wrong. Like, I think you just put all the weights in a box, and then, like, each layer of the network is, like, a matrix multiplication with the last layer, I think. But I could be, not sure. I have to look into it a little more. Okay, let's for now say weights is equal to 0, 0, and biases is equal to 0, 0. Easy peasy. And so, what are we expecting to get here? It said 0.5, which is actually surprising. I would have expected 0. Oh, because we're running it through sigmoid, right? So we get 0 as the output, we shove that into the sigmoid, and the sigmoid is 0.5 at 0, so that this is reasonable. This is like, we're running through the stuff. Now, this is not very useful, right? Because if we want to do backpropagation here, what the fuck are we gonna do? We don't know what's going on, right? We would just have like floating point numbers. Ew, gross. So I think what we need is some sort of like, I don't know, some sort of like number where we can track the graph of what happened to him, right? So like when we do backpropagation, eventually we're going to be like, we're gonna get to the end and we're gonna be like, loss. What was my loss? And we can be like, we need to be like, how did we get here? Right? And we're gonna go like backwards. So like backwards, we're gonna have like some sort of like, I guess like the loss is gonna be, in this scenario, we're kind of lucky that our loss is just how far off were we from the right answer. So we're gonna be like, was the correct answer 1 or 0? And we can probably just do like, you know, what did we get? X, and like subtract it from this and then like absolute value it. But, you know, maybe that's like not as nice as squaring it because mean squared error is a thing that you'll see later where we do like add up all of the things that we got wrong, square them all so that like it has some nice properties. One is that squared is always positive. Two is that it like amplifies big errors more so that they kind of like contribute more, and so we like focus more on things that are really wrong than things that aren't really wrong. So let's do this. This is also like, I know how to differentiate this, where differentiating abs, I guess I know how to do that too, but this one's really simple. You just bring the 2 down, right? So let's do this. Let's do this. So we're going to need to say that like we calculated the loss, right? And that was like made up of some inputs, and we need to like find the derivative of that. And then that went through like sigmoid, and then that went through some like multiply or add, and we're gonna have to like figure out like how we got here. So I think I want some sort of like net, like just like linked list of nodes seems kind of reasonable. I know this isn't how you would do it later, but we're trying to think of some structure where when we're calculating derivatives, we only have to calculate each one once. So having some sort of like way to track that seems nice. And then like it later as well, if we had like 2 things that we were trying to like track here, can I just like bring this down? Right, like you're gonna have like many computations branching off like the same point, right? With like other inputs from here and here, right? And so like understanding that like we only need to calculate the derivative of this guy once. I feel like this is very like node graphy, you know? That's just kind of how I'm feeling. So let's say that we have some tracked floating point number. Okay, and he has a pointer to like where he came from, right? So let's see, what do we support right now? We have sigmoid, we have multiply, which this takes like a times b. We have add, this takes a times b, right? This takes in single parameter, and then our loss function is like a sum of a bunch of things. So you can say if we're summing, you know, a plus b plus c plus d, right? You can compose this of like many sums, right? This can be like sum of this, then sum of this, right? And then sum of this. So everything can be represented as 2 numbers, I think. So let's say that we have in 1 is a pointer to another tracked floating point 32. In 2 is a pointer like optional pointer because it might not exist. I guess both of these might be optional, right? Because like maybe you just have like a constant, but maybe your constants, yeah, they might be, we might need them, so not sure. And then we have value, which is an F32. This might be fucking stupid, but you know, whatever. Well, later this will get like optimized into something much better, but this is like the way that the problem makes sense in my brain right now. And then we need some sort of like operation that we apply to this thing, right? So operation, I guess. And for now, I think that, you know, just having an enum of all operations that we could do seems reasonable. Maybe it's not, but maybe it is. And like right now, what are we gonna do? We have like add, we have mul, we have sigmoid. Right? And then like square, like pow as well, I think, to do loss. Something like that. right? And so now all we need to do is like say, how do I make this thing, right? So init from, val is an F32, it gives me one of these guys, and I guess we have init as one operation here as well. I think that's reasonable. So this guy's like I have val is val, up equals init. We have in1 is null and in2 is null in this scenario because there are no inputs to initialization. This value just came from fucking nowhere. We have add, so we take in self as a tracked F32, pointer, not pointer, pointer. And we have A, which is also tracked F32, and B, which is I think it's actually A and B, no self. Yes. So this will return a new tracked F32. Maybe as a pointer. I think using pointers everywhere is going to make this easier. So, because like we can then just like slap them on some allocator, reset the allocator every once in a while, whatever. But like that way, I think it makes sense that way. Because these things need to have stable memory locations so that we can like do the backpropagation. So I think this makes sense. Let's do it this way. Let's do it this way. And so here we're going to be like, what? We have val is a val plus b val. Easy. Easy, easy, easy. No way of doing ends in C. It's actually in Zig, but very close. Very close. Basically the same shit. So I think it's just like this, right? In 1 is A, in 2 is B. And then we can kind of just walk backwards from there. Simple. And we need to return these guys we need to allocate, right? So unfortunately that means that everything is gonna have tries everywhere, but like fuck it, I guess, whatever. And I guess we do like ret is try stood alloc create. One of these guys. Sure. Ret.star is equal to this, and then return ret. Okay. This seems reasonable so far. So far. Oops. Sure. And okay, now we just start slapping in different guys, right? So multiply is A times B. Okay. And sigmoid. Sigmoid is only single parameter in, so in2 is null. We forgot to change this guy to say that he was a multiplication. And this is sigmoid of this guy. Okay. Easy peasy. Yeah, sorry, by the way, I apologize for you guys if you are saying stuff in chat and I'm ignoring it. It's because I'm too stupid to work on this and answer and read chat at the same time. So I apologize. I understand that that's maybe not great. This is ambiguous, huh? So can we do, how do I disambiguate this? What if we just don't? The easy fix is to do this. Easy. Actually, maybe we should leave this function here, though. Oh, I guess we can actually do tracked F32 dot, or no, fuck. That's the one we don't want. Yeah, I'm just gonna copy paste it because I don't want to think about namespacing right now. This is not important. Not important. Okay. Do I understand correctly they're gonna use deep learning to recognize barcodes? That's so neat. That's where we're gonna end up, yeah. Why did you use Zig? Just because it's like the language I work in right now. It's the one I find most satisfying. It has like a bunch of like attributes that just line up with my current value system. Okay, last one is power. Power. So we have pow, A and B. And this is gonna be stood math pow, A, B. We're saying that this is pow, A, and B are our two inputs. And now this should be everything that we need to like walk backwards. Regraphics, the relations that you can package all parameters of a node, weights and biases in a single matrix, just like you can package general graphics transformations in a single matrix. Yeah, agreed. In both cases, you need a pad input with a homogeneous one for stuff to work out. Okay, that's not my understanding. Oh, I see. I understand now. You're saying that you can put weight 1, bias 1, weight 2, bias 2 in the same matrix. And so for you to use this guy, your inputs are, you need to throw the 1 into the bottom to make the bias work out. I was thinking of it as like weights plus biases in its own vector. You know what I mean? Like in its own matrix. But I understand what you're talking about now. I understand. Okay. So this guy works with tracked F32s now everywhere, right? And we are going to be like, each of these is now like this. But this needs to come from some allocator. Sure. And is that true? I think so. Fuck it. You know, fuck it. That's what I always say. Okay. Cool. And so now here, instead of doing this stuff, we are running the network here. So we have like a tracked, I guess, is, we need an allocator here as well, is tracked F32 and an A, B tracked is B. Okay. Then we can do self weights 0, mul, A tracked. Okay. Then we add to that number self biases 0. Okay. A out or something. For B, we do 1, B, 1. Okay. And then we return A. We return the sigmoid. So tracked F32 sigmoid of A out add B out. Okay. Yeah. So far, looking kind of good. So far that looks reasonable. Now, if this guy is still doing all the right math, we should be able to see the same 0.5 here at the end. We do need an allocator, so var mem heap arena allocator initialized backed by the page allocator. Eventually, we'll probably pull in our allocator system, but for now, this will do. I think. And let's just see if this compiles and runs. No, because everyone here needs to be tried. Everyone needs to be tried. Okay, so blah blah blah, expected this. This guy is failable, true, because allocations can fail, and these guys are returning pointers now. These guys are all pointer returns, so we're chilling. 89 is mad because these guys need to be pointers here. Okay. Sure. Run needs an allocator. Okay. And no field name mul in track 3 F32. Okay, so why not? Because I took in the allocator as the first guy like a dumbass. Okay. This kind of blows having to like pass this allocator everywhere, but it's fine. Okay, we'll work with it for now. Tracked F32 mul alloc weights a tracked. Okay. Yeah, this sucks for composition. This really sucks. Can we? So it will be useful in the future to be able to like nuke sections of the graph at a time, right? Like the weights for the network, we kind of want them to live in a different lifetime than all of the downstream stuff that comes from them, I think. But for now, we'll just do it like this. It's fine. We'll find, well, because this, tracked F32, add Alec, this thing, like this. Okay. Yeah, we can make that work for now. And then, why is he mad? Okay. Yep. And then B out looks similar, but with some ones kicking around here. Uh-huh. And then this needs Alec, A out, B out. All right. We, A out, nope, 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 nope. This is A out, add B out. There we go. Okay. Are we close? Fine. Okay, so we still get 0.5 here, which is a good indicator that we haven't really fucked this up, and it might be nice to, like, look to see if we have, like, the correct chain of actions, right? So can we say, like, who did this guy come from? Yeah. So can we say, like, like print net or something. I don't know, man. Or yeah. Yeah, sure. Print the network of stuff that happened. So we're gonna have some like input as a tracked F32, and we're gonna return nothing. We're just gonna print stuff. And I think we're gonna have like an indent level here, certainly, because this is gonna be like some sort of tree walk, probably. And we're gonna be like, I guess we print the input, this thing, right? So it's like probably some name with some value, I guess, is what makes sense here, right? So like, you know, we're gonna start with, you know, tag name of input op. So this was like some operation that came from these guys. So he's, oh, this is his value. Yeah. And then I guess we're gonna say like if, input, you know, in 1, we print the network again, but with the indent level up by 1. And this we print in 1. And then we go into, okay, yeah, okay, that's reasonable so far. And then here, I guess we have to say like for 0 to indent level, we print some tabs, I guess. I don't know, man. Print net output. Close. Okay. So this sigmoid came from an add. This sigmoid came from an add who had 2 parameters, which came from a multiplication with 0 and some 2 parameters. Oh no, sorry. This add came from this multiply and this initializer. So this is the bias 1. This is weight 1. This is this is our parameter input. This is weight 2, parameter input, bias 2. I think this is right. I think we have a graph of how we got to this answer. And so now we just need to throw on the last piece here. So we can say loss is going to be like our expected answer. Okay. So we're expecting 3 to be less than 10, so this should be 0. Right? And we're gonna say This is the expected. Okay. Loss is going to be something. Something, something, something. Let me think. My poor stupid little brain. Expected sub. We need sub. Which I think is kind of just an add if you think about it. I think. I guess it's like multiply by -1 and sub, and then add. So I guess having sub in here is fine. Having a function for sub will make our lives easier, so we just do this. Sub, minus. Okay. So this is expected. This is going to get old fast, but whatever. For now. And then we square this. Pow. And then we do init too. Okay. Okay. So does that work a little better? Fuck. Pow is mad because stdmath pow requires us to pass in the type that we're powering, which is fine. We'll live. And this needs vowels here and here. Okay, so we have power 0.25, which comes from subtracting 0.5 from 2. That 2 seems wrong, no? Oh, I see, my bad. This is a power of this to 2, right, which we're subtracting the correct answer 0 from the sigmoid of 0.5, and that's coming from an add of these two numbers. Okay, got it. This seems right. I think this is the correct chain of actions. Which means that our forward pass is done. So, back propagation. What do we need to do here? Remember, we said before that, like, we get there by finding, like, the derivative of each of these guys and multiplying them with the derivative of the guy previous. Right? So, what we need to do, I guess, is request the derivative of this guy. Yes. Yeah. So, what does that mean? I don't know. Where's this gonna go? I have no fucking idea right now. I have no fucking idea. But we will see. So switch on our operation, right? The derivative is gonna be different for each one. And I guess we need to think about, okay, so if I do A plus B, how much does a change in A affect the final answer? It's 1, right? It's just 1. Like, if I move A up by 1, that changes the final answer by 1. I think that's right. If I have A plus 2B, how much does a change in B change the final answer? Well, then it's like 2 times B. Yeah, so I think... Okay, so that makes sense. If I'm looking for the derivative of like a single parameter, that's like easy to calculate. Now, if you have like a multiplication of 2 parameters, A, B, we need to like determine which of these 2 parameters we want to be deriving for, right? Like, any change in B will move A in that direction, and any change in A will move B in that direction. So I guess here we need like an index. Or maybe we don't calculate derivative here. Maybe we do backprop. Maybe we just do backprop and tract F32 can like own a like gradient thing here that is by default initialized to null. Okay, yep, that makes sense. And for now, I'm actually just going to write equals null here. Okay. What keyboard do you use? It's just like a 60% cherry brown keyboard. Okay, so what we'll do here is when we backprop, we're basically going to be doing the same thing as when we print the network, right? We're going to go through each of our parents, check if we've already calculated the gradient because we got there through some other path, which is very possible. And if we haven't, calculate it. Okay, cool. And then we should be able to know how this parameter affects the final output. Is that true? Do we need gradient with respect to each value here? We might. So how does a change in 1 affect my output? How does a change it to 2 affect my output? That feels more like my mental model of this, right? We have A, B. How does a change in A affect the final output? How does a change in B affect the final output? Like, that depends on how they're used downstream, right? So I think that that makes sense. I don't think that, like, A doesn't have, like, a single gradient value, right? He kind of has, like, a gradient value with respect to how he's used, I think. Maybe I'm wrong. Maybe I'm wrong. But this is what seems reasonable to me right now. Okay, so when we do backprop, we so add is simple. Let's just start with add and then work our way forwards from there. So I guess this thing's a pointer probably, and we have like, all right, I guess init is return. This is our exit case, right? We've hit a number that has no one who he came from. He's just like some base number. Um, Fuck. Because we need like the power that came in here. So can we say that into? We'll just do this for now. We need to write down what the power was. So can we just do like into raw is equal to b for now, and then we can say, the gradient here is
Fire TV has so many great recommendations.
Yeah, serves up the best options from all my apps in one place. It's like it knows what I want to watch before I do.
The orangutans have escaped the zoo. They're everywhere!
Picture quality is amazing, so lifelike.
Yeah, you can search by genre, movie, actor.
Huh, that's convenient.
Alexa, show me the latest hit movies.
Sweet.
Get into more of what you're into with Fire TV.
matters. I don't think you should care what my keyboard is. Because I just like fucking Googled 60% keyboard and then picked one. Like, I don't do like, my purchasing is like fucking stupid. Okay, sub. I think that this is the same as add, but one of these is negative, right? So yeah, I think it's like this. I think. I don't know, but that seems kind of reasonable. And then the only thing we're missing is sigmoid. So sigmoid derivative, I'm sure we can just like sigmoid derivative. Blah blah blah. Differentiate is sigmoid x times, oh wait. No, that's not the answer. Wait, maybe it is? Can we just like derivative of sigmoid? Does it just tell me? Yes. Derivative is e to the negative x over e to the negative x plus 1 squared. Alternate forms? Sure. Okay. It's this. So x is, I guess, yeah, it must be N1 val here. Yes. And then we have e to the negative x over e negative x is this. So it's e and x over e and x plus 1. And it's like this, I think, right? Because that's squared on the bottom. Yeah. Okay. I think that's right. Fuck it. Okay, so down here, this pow now can just be a 2 like this. Okay, and then can we call, like, print the back prop? And I guess for each of these things, can we print the gradient as well? Yeah. Okay. Okay, yeah, so the fact that we see zeros all the way down seems pretty wrong. Gradient 0 everywhere seems incorrect. So we must be doing something wrong. I would like to work our way down, like, let's just do like a more simple problem. Right? Can we say X is a tracked F32. Okay? And P is the result of like a multiplication of two numbers. Okay, so like 3 and 4. Okay, simple, right? We backprop here and we print this thing. Okay, let's start here. So we have 12 comes from 3 and 4. So what we're expecting to see here is that any change in 3 is like has the derivative of 4, right? We want him to be like any change in this results in 4 times that output here. And any change in this results in 3 times the output up here. That's what I would expect to see if I understand all this correctly, which very well I might not. And so the question is, why the fuck isn't that happening, right? So we come down here to mul. Hello, what is fucking that there was like some like stuff hanging around there from bad rendering. So oh, we're not recursing. Yeah, that's why. So we need to do in one backprop and in two backprop. So we need to do that here, here. This one only has in one. This one has in one and in two, and this one's in one. Still no, huh? Backprop. Let's start here. And can we say what operation this is? Backprop mul, backprop init. So we're actually getting here, right? We should be here, and we like, why is this not doing anything then? Oh, val here, not gradient. Oops. Whoopies. Whoopies. Nice. Okay, so this makes sense to me, right? Any change to the number 3 will result in a 4 change in 12, and any result of 4 will result in 3 change in 12. That, I think, makes sense. I think. And we can confirm that this is right by changing that value on its own and seeing that the net amount it changed is the same as what the gradient says, right? So here, if we change 4 to 5, we should see this go up by 3, and this should become 15, right? Which is obviously true, but we can confirm that, right? And as we get into more complicated cases, we can like get a little farther down, right? So let's say, like, let's go back to our more complicated thing. Right, so we run our network on these two numbers. We say, hey, how does this thing change the answer? I need to print the network. Oops. From loss. Okay, so here we go. Like, if we change the value, hold on. If we change, it's so hard to track what each of these things are. Should we add names to them? We could add names to them to make the things a little easier. Or we could actually just do this. Let me print the gradients for network weights 0. Right? So we think that if we change weight 0 by 1, the output number should change by 3. Which seems impossible to me. That seems impossible, right? Because the output is a number between 0 and 1. Because we were supposed to multiply this by his parent gradient. Or downstream gradient. Right? So each of these things, we're like differentiating that thing on its own, but his gradient is added multiplied by my own gradient, which I don't know yet until Yeah. Yeah, there's something weird here. Like, I can only differentiate, like, until I've looked at the whole graph. Oh, god damn it. It's like, as we walk, we have to do gradient accumulation or something. Yeah, there's something there. There's something there where, so like, I know that the derivative of 3x is 3, right? But I need to multiply that by the derivatives on the way up. And so like, on my graph of stuff that happened, loss, oh my god, my fucking scroll wheel is broken. Loss, sigmoid, you know, whatever. As I like go down this chain while I'm printing, do I multiply gradients together? But even that doesn't really make sense, because here when we're adding to the gradient, he needs to be multiplied, like, he needs to be multiplied by how much he contributes. So it's almost like before we go down a layer, we need to know. Hold on. Hold on. So the idea here, like, if we have A is used in like 2 things, his contribution to this, or to like the final answer, I guess, like both of these are used in something here. His contribution is only known once we know his contribution, which is only known after, you know, if this network kind of went like this, right, where he's used in like 2 things that are used in the final answer, like, we only know his contribution once we know both of these guys' contributions, right? So we can't kind of do depth first search, you know what I mean? You have to do breadth first, so that you make sure that, like, but even then, like, I don't know if these things come in like nice clean layers like this necessarily, right? Because like, what if he's like this? Like, then what? You know? So that's kind of interesting. Okay. So what if we change the rules? What if we calculate the... What if we don't, like, accumulate him? Well, we have to somehow. Because, like, the answer that we want to know at the very end... The answer that we want to know at the end is how much does this affect the final answer? Which is the sum of how much he affects this and how much he affects this. And so the add thing does make sense there. It does. But it's that we have to know that, like, it's complete. Okay, so I think it's easy to know. It's easy to follow this chain back, and it's easy to know that when I get here, I can say how much does this affect this answer through this chain. That's like a very like easy to do operation. Which means that we have everything we need if we walk the whole graph. So it's that like backprop needs like to take in like parent amount or something. You know what I mean? Like, or like downstream gradient. How much does this affect? How much is this affected everywhere else? And here we just multiply everything by downstream gradient. Every time we modify these guys, I think that makes sense. Yeah. And then as we continue down, yeah. So in one grad is this. Okay, this seems like it goes somewhere. This seems like it goes somewhere, right? And then we pass in one grad here, and then it kind of just like makes it all the way down. Are you just building an info, or do you have a training target in mind? The barcode scanner. We're eventually going to get to the barcode scanner. The optimization benefits of single layer training are hard to overlook. I agree. I agree. I just want, like, eventually this is going to turn into, like, GPU training, probably. But I just want to get, like, the basic idea down first. You know what I mean? So that, like, I have a better handle on it. I feel like doing, like, the stupid slow thing first and then optimizing later will result in, like, a better answer. You know what I mean? You know what I mean? Because, like, stuff like this, I wouldn't, like, understand yet. That, like, this is, like, a like, this is a discovery that I'm making right now. Are you actually? Are you realize I'm showing? It's like a funny chain of events. It's, like, not actually because it's, like, the right answer. I understand that. Okay. In 2 grad is this. And in 2 grad. And then in 1 grad, in 2 grad. I think that this makes sense. I think, but we will see. Guy wants to track calories for the app. You need barcodes. Gonna need neural network. Yep. Exactly. Simple. Okay. Boom, boom, boom. Okay. In 1 grad here is this stuff, which goes in here and here. This is in 2 grad equals this stuff. Yep. And please God, tell me we're almost there. Almost. Okay. Boom. 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 Okay. And then here, this is 1.0 for the initial multiplier. Okay, this looks... Oh, wait, hold on. What is happening here? Okay, yeah, so this is saying that changing the weight by 1 will have an increase in the final answer by 0.75. So here is the, like, loss. Yeah, okay. So we're saying if we change weight 1 by 1, this will end up at the answer of 1. I think that's what it's saying, which we can find out, right? We just put a 1 in here. And no. That is not what happened, which makes sense because that would be, like, quite extreme. Oh, no, sorry. Oh, no, yeah, 0.75. And then this one also is, like, 2.5 is wrong. So we've still done something wrong here. I really thought this, like, going down would make sense. It felt right to me. It felt right, but now I'm not 100% sure. Can we go back to, like, a simpler case? Can we go back to a simpler case? Okay, so in this simple multiply, a change in 3 by some amount will go up by 5. Okay, let's try to do something like, can we divide this entire answer by 0.5? You know what I mean? Or sorry, divide by 2, multiply by 0.5. So my understanding, if we do this, is that the amount of change for each of these guys is going to be halved. Right? So here, you know, the total answer of changing 3 by 1 should be that this goes up by 2.5, right? So change this to a 4 and we should get to 10. Okay, so that's good. This seems to work the way I would expect. Now, can we try adding in, like, some other operations, right? It's very likely that some other operation is fucking us here. So can we now do, I don't know, try track def32 pow. So let's take the power of this to 2. Okay. Cool. Okay, so here we're saying that like a change in 4 by 1 will increase this by 50. So change this to 5. We should see 150 here. Okay, that's not quite right. So that's interesting. That's interesting. So, oh, but of course. Of course. Okay, I'm a dumbass. Wait, this might just be working correctly. Of course. So, if I am on some like parabola, and right here, we say, hey, a change going over by 1 will result in us going here. Like, that's not true, right? Because in real life, like that's the derivative is only correct for an infinitesimally small movement, right? And so if we have like a real parabola, the real change is like more than that, right? So I think this might just be right, right? Because we overshot by our estimate by a little bit, as expected. Oh, Christoph, thank you for the raid. Sorry I missed that. Appreciate it. For those of you who came in, I apologize. You've probably been watching for 5 minutes being like, he's just talking, but we're trying to train a neural network from scratch. And we are just starting to get through like backpropagation, right? So we have a series of operations that happen. We kind of like build a node graph of all of those operations. And then we say, how much did this piece of that node graph contribute to the final answer? And we're doing that with like, you know, we have derivatives for each of the operations that we support right now. This is not how this will end up, but this is how it works for now. And yeah, we are then going to try to train something with that, but we're not there yet. Okay, so I think this might be working. Maybe. I mean, it's not like we could write some tests. But what if we just fucking winged it, you know? Yeah, fuck it. Let's see if we can get this to do the thing that we wanted it to do, right? So we say, hey, we have two numbers. We want to know which one is bigger. We have gradients now, like theoretically, assuming that we did everything right. And so let's do a training loop. So our training loop is probably, oopsies, wrong thing. Okay, can we, first of all, say we have like a loop arena? Right, a lot of the calculations that we're doing here are going to live in one batch of allocations. All of this stuff per training loop. And we're going to say, we're going to keep looking at like one number. We're going to keep doing this maybe once. Maybe we do like 10 iterations at once or something. Both of those are very reasonable answers. And then we will try to like nudge the weights and biases a little bit so that they look a little bit more right. I think that's reasonable. Because we have like a direction to move now, right? So we say like, while true, we pick two numbers, any two numbers. So we need something like RNG. Stood random default PRNG initialized to 0. I don't give a fuck. We pull up the random interface here, and on each iteration of the loop, we say, let's run this guy with A and B, right? So this is gonna be a rand float. B is a random float, and we're gonna throw A and B in there, right? I do want to scope these a little bit because I'm worried about getting like really big numbers and then getting nans. But I guess we can just say like, if kind of like run this whole thing and then check for nan at the end, I guess. Right? So we can say, if loss val, like, what is it, like stood math is nan or something? Yeah. Probably or infinity or something like that, whatever. This will work for now. Okay. So let's start here. Let's just run in a loop and, okay, everything in here gets loop arena now. Boom, 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 boom. And then at the end of the loop, we do reset. Retain capacity, I think is fine. Okay, so here we're seeing numbers here come in. Nice. So we have our numbers coming in, and we're seeing that the gradients are changing a little bit. Now what I want to do is like just do a stupid thing. The real world of neural network training uses these things called optimizers, where they kind of like use some heuristics to figure out how to move each of these weights according to the gradients, right? Right now we have the information of like, how much does an infinitesimally small change in this thing affect the final answer? And I suspect that if we do the stupid thing of just nudging everything in lockstep, we're not gonna like really get a great answer. You can kind of imagine that maybe you want some like momentum to these things, right? So if they keep going over and over and over again, we're like, we need to keep going that way. You might want to speed up so that you get there faster. You might want to maybe only do some parameters at a time because like maybe changing 2 in lockstep is different than changing this guy without that guy, right? Like because of the fact that our gradients, you know, for parameter A depends on parameter B, right? Like maybe you wouldn't want to move them all at once every time. Maybe you want to do some subset. There are all sorts of like heuristics you could probably use, and I know that there are optimizers that people favor. But for now, let's just say we'll step every fucking weight in a direction by some amount, right? So we can say like net dot optimize. Yeah, we net optimize. And here, I guess, for now, we will look at like for self weights. Wait. I think we might have to put an ampersand here. Can we just say like we have some like learning rate, right? So like really small number, bump it like a little bit in the right direction, and we say like self or like W is equal to W gradient times learning rate. Plus equals. Yeah, so just like nudge in that direction. We do the same for the biases. Sure, fuck it. Whoa, what's he pissed about? W val biases, bases, biases. True, so true right now. But he's mad about like a double pointer here, which I'm confused about. Oh, because this is already a pointer. My bad. Right, of course. It's already a pointer. It's an array of pointers. Okay, so what I want to know is, are these numbers getting more reasonable over time? So if we run this thing, if we just look at like this like top number here, we can see that this value is getting closer and closer to 1. Eventually it becomes 1 actually, which is interesting. So maybe it'd be interesting to look at the weights here. That like indicates that we're getting very close to, oh. Hold on. We want the value to go to 0, no? We want the value to go to 0? So does that mean we're supposed to minus equals this shit? Yeah, here we go. We got this thing close to 0. Hype. Okay, so can we print the 2 weights? We're doing gradient ascent. I think we want minus equals. Yeah, I agree. Dude, it's so sick. Not that like, I'm surprised that somebody can watch me just talking out loud, just bumbling around like a fucking idiot, and like understand enough to like correct the problem before I notice it. Like, that's so sick. That's so cool. Like, I don't know like what part of that is cool. It's just like surprising to me because I would think that if I just like bumble around like a fucking idiot, I'd be so lost in the sauce that like you can't tell. But it's kind of sick that like that indicates that there's at least enough human communication going on that like there's something of value here, and that's cool. I just think that's exciting. Anyways, that's sick. Okay. Value close to 0. And so what I want to do now is I guess look at the weights and biases. That would be kind of interesting to me. So can we look at like what does this thing learn? Because what I would have expected, from going way back to the start of this thing, I would expect that, you know, you have A coming in, you have B coming in, right? They're both coming in here. What can we like multiply, add to get this to go to 1 if A is bigger and 0 if B is greater? I think my assumption here is that you have weight 1 is like approximately equal to weight 2, but negative, right? And then that way, when this is greater than 0, A is bigger, and when it's less than 0, B is greater. That would be like kind of my assumption here of what it would learn, but we don't actually know, right? But let's kind of see if that, like, our guess is good. So can we print maybe just the whole network here as well? Net. Okay, so give a second, hit Control C. Our loss is quite low. However, I guess that we don't really know if it's only low for this particular result. But, you know, we can probably hope. And so let's see, what do we get here? We get our weights here. Weight 1 is negative 2.1. Weight 2 is also negative 2.1. That's interesting. The biases here. Wait, is that true? This is one thing. This is the other thing. Biases is negative 4 and negative 4. So these guys are actually getting the same. They're actually coming into the exact same thing. Why are you assuming 0? Yeah, that's a really good point, huh? That's a really good point. If A is greater than B, expect... Yeah. That's a really good point. I'm surprised that it's converging on anything, actually, now that you think about this. So if A is greater than B, we should be like... I guess just like this. So if A is greater than B, 1. Else 0. And then I guess like if A equals B, like let's just it's fine. It's fine.